Welcome to the tutorial on Booth's algorithm. The purpose of Booth's algorithm is that it allows us to multiply signed binary numbers in 2's complement form. It is actually an improvement over the unsigned binary multiplication method, and we will see how in the following slide. The context of Booth's formulating this algorithm is one in which the observation was made that an ALU that could add or subtract could get the same result in more than one way. It was also noted that the operation of shifting was faster than that of addition. Therefore, by producing an algorithm that eliminated or at least reduced the number of additions that would take place, would increase system performance. And this is what Booth's algorithm actually helped to achieve. The requirements of Booth's algorithm are two numbers, such that one is a multiplicand and another is a multiplier. We'll also keep a count of the bit lengths of each of these numbers, and we will see how we will use that at the end of the process of applying Booth's algorithm. Booth's algorithm utilizes variables A, the accumulator, Q, the multiplier, Q minus 1, which is a new addition to the algorithm, and this is where it begins to differ from the algorithm presented for the unsigned binary multiplication tutorial. And following that, we have the multiplicand. We notice that, as before, the multiplicand is a fixed value. However, the variables in A, Q, and Q minus 1 change throughout the application of Booth's algorithm. We notice also that there are quite a number of cycles which we have to go through, and along the way we are performing either subtraction, a shift, or an addition. We note also that after each cycle, we will perform a shift. The initial values of AQ, Q minus 1, and M are shown here. In order to determine whether we are going to add to the value stored in A, or to subtract from the value stored in A, or to do nothing other than a shift, we need to compare two variables. We are going to compare the least significant bit of the column Q, that is the rightmost digit, with the content of column Q minus 1. And we are looking for differences and similarities. Because we're comparing 2-bit numbers, there are 4 possible combinations with which we will deal. When the least significant bit of Q matches the least significant bit of Q minus 1, we will not perform any addition or subtraction. When they are different, we introduce the addition or subtraction. And after all of these operations, we perform a shift. So whether the numbers differ or are the same, regardless, a shift operation will be performed. We notice that as per the initial values, the least significant bit of Q is 1 and the least significant bit of Q minus 1 is 0. So we are going to perform a subtraction as per the conditions. And we will be subtracting from A the 2's complement value. We will be subtracting from A M and saving that value in the A column. This M, negative M, represents the 2's complement value of M, and therefore once we convert M to its 2's complement form, we can perform an addition to the previous value of A and store that on the current line, and that is exactly what is done. Again, we take the 2's complement value of m, add that to the previous value of a, and store the value of a. Having performed this operation, we then move to a shift. I do have to note that because we want to preserve the integrity of the content in the accumulators column, when we are performing our right shift in this column, the most significant bit remains unchanged, such that we would shift the 1, 0, and 0 to the right, but leave a 1 as the most significant bit. We're shifting so the columns that are affected are A, Q, and M, such that the least significant bit of A becomes the most significant bit of Q, and the least significant bit of Q becomes the most significant bit of the column Q minus 1. In our second cycle, we note that Q and Q minus 1, the least significant bit of Q and the bit stored in Q minus 1 from the previous cycle are in fact the same. So this means that in this cycle we will not perform an addition or subtraction, but we will perform a shift. Again, we want to preserve the integrity of the data stored in this column, so we keep a 1 in this place, we shift the other 2, and make the least significant bit 0, the most significant bit here, and make what was the least significant bit of Q the most significant bit of Q minus 1. After performing our shift, we compare 0, the least significant bit of Q, with Q minus 1, and it indicates to us that we are to perform an addition and store the sum of A and M in the accumulators column, and that's exactly what is done. An easy way to remember whether we are to add or to perform is to think of what a digit or a binary number beginning with a 0 or 1 would represent in 2's complement form. For instance, as a general rule, any negative number begins with a 1. If we were to group the bits, the least significant bit of Q with the bit in Q minus 1, such that that would give us a binary number, we notice that the most significant bit in the number 1, 0 is 1, and this would denote a negation, and it implies that we perform a subtraction, and that's what the operation is in the first cycle, a subtraction. Similarly, if we jump to the third cycle and we compare the least significant bit Q with the content of Q minus 1, we group them such that we form a number 0, 1, a binary number 0, 1, and we evaluate the most significant bit of that number. We find that it is 0, and with respect to 2's complement form, any binary number which begins with a 0 is a positive number, and therefore this grouping 0, 1 denotes an addition, a positive operation. And so we will add to A the value of M and store the result in A. So that's an easy way to remember what operations are to be performed when. The number of cycles is 4 because they correspond to the number of digits in our multiplier. Additionally, we notice that at the end of our fourth cycle, there are non-zero values in the accumulators column, Q column, and I specifically pointed these out because, as I said before, when we began, and we picked our multiplier and our multiplicand, you were told to keep account of the number of digits in each of these. And here's why. The number of digits in the final product would be equal to the number of digits, also known as a bit length, of the sum, or the sum of the bit length of the original numbers. So we had 4 numbers in Q and 4 numbers in M when we started, 4 digits in M. 4 plus 4 is 8, so our final answer should have a total of 8 digits. And it is the case that our product is indeed going to have 8 digits, where the most significant bits of that product will be read from the accumulators column, and the least significant bits will be read from the multipliers column, such that after operations of addition and subtraction in 4 cycles, the final answer is 0, 0, 0, 1, 0, 1, 0, 1. And this is Booth's algorithm. A little bit of homework for you. Try multiplying -7 and 3. Here are some guidelines. Begin by converting 7 to binary form, and then find the 2's complement of 7. Let that number represent the multiplicand. Work through the steps as normal, and see the attached example for more information. On behalf of the Comp 2125 Learning Corner, I am James Morris.